Welcome to The Explainer. So today we're diving straight into what is honestly a technological holy grail. We have these incredibly powerful quantum processors, but getting them to actually talk to each other, well, that's been a monumental challenge, until now. Today we're exploring the exact breakthrough that's overcoming the biggest obstacle to the quantum internet, maintaining coherence during microwave-to-optical state conversion. We are looking at the tech making a fully functional, highly scalable quantum internet a reality.
Okay, let's dive into this. We'll start with the quantum internet vision, then look at the translation bottleneck holding us back, explore the TFLN breakthrough, and finally, wrap up with how this actually builds scalable networks.
So it's the million-dollar question, right? Why don't we have a quantum internet yet? I mean, we hear about new quantum computers all the time, but without a way to connect them, they're really just isolated islands of immense computing power.
All right, Section 1, the quantum internet vision and connecting distant processors.
Basically, a practical quantum internet requires taking isolated quantum processors and linking them together over vast distances. Think about our current classical internet for a second. Its power doesn't just come from individual computers, it comes from the massive optical networks, the fiber optic cables that connect them all globally. To realize the true potential of quantum technology, we absolutely have to achieve that exact same global connectivity, but for incredibly fragile quantum states.
The vision really boils down to three core goals: connect distant processors, build a truly practical quantum internet, and importantly, create a fault-tolerant infrastructure. Now, fault-tolerant just means a network that's robust enough to handle super delicate quantum information without everything falling apart. These macro goals kind of laid the groundwork for understanding exactly why a specific microscopic technological missing link is currently holding us back.
Let's move to Section 2 and see how this builds. The translation bottleneck, or the missing link.
And this brilliantly illustrates the core of the problem. We are dealing with two completely different physical domains. See, processors compute using microwave qubits, but data travels through optical fibers using optical photons. So there are, essentially speaking, two completely different languages. It's kind of like trying to order a coffee in a foreign language using a terrible translation app. Right now, they desperately need a universal translator.
This urgent need for a universal translator brings us to quantum transduction. This is simply the process of converting a quantum state from one physical domain to another without losing the fragile quantum information. It's translation. But here's the catch. Unlike copying a regular digital file, if that delicate quantum state collapses during the translation process, the information just vanishes forever.
So why is this so hard? Well, current quantum systems struggle massively with scaling due to three main issues: thermal noise, interconnect losses, and the destruction of coherence during this frequency conversion. Imagine a translator trying to do their job in an incredibly noisy, chaotic room. They can't hear properly, words get lost, and the final translation is completely garbled. That thermal noise and those physical interconnect losses are exactly that noisy room, causing the destruction of that fragile quantum coherence.
Which leads us to Section 3, the TFLN breakthrough, Thin-Film Lithium Niobate.
Enter the Imagenta hybrid platform. This uses a highly specialized material called Thin-Film Lithium Niobates, or TFLN for short. This is the missing link we've been looking for. It allows us to build advanced quantum transducers that enable coherent microwave-to-optical conversion so the processor and the network can actually seamlessly talk to each other.
Now, to understand why TFLN is the hero here, we have to look at the villain: parasitic acoustic coupling. Put simply, these are just bad vibrations. Destructive physical vibrations that act as intense noise and destroy quantum coherence during the translation process. These vibrations are the primary cause of the thermal noise and interconnect losses we discussed earlier. If you can't stop these bad vibrations, the data is gone.
But this is where the engineering gets fascinating. The Imagenta hybrid uses optimized phononic crystal geometries to actively suppress that parasitic acoustic coupling. By perfectly shaping these crystals, they essentially create a vital vibration shield. It ensures the quantum information survives the conversion intact, totally shielded from the destructive noise. So it plays out in a simple three-step recipe. Step 1, you input the computing information, the microwave qubit. Step 2, the phonic crystals do their job, suppressing the noise to maintain coherence during the frequency conversion. And step 3, output a perfect, highly stable optical photon ready to travel across the network. What makes these TFLN transducers so incredibly revolutionary isn't just that they work, it's how well they work. They allow for high rates data transfer in a low-noise environment. But the absolute game changer here?
This enables high-fidelity, low-noise bidirectional conversion between microwave qubits and optical photons. This isn't just a one-way street. Information can flow from microwave to optical and right back from optical to microwave. That bidirectionality is what makes true interactive network communication possible.
All right, Section 4. Building scalable networks through on-chip integration.
Now, what's really interesting here is the phrase existing fabrication processes. The TFLN design actually supports scalable, on-chip integration using manufacturing methods we already have today. This is massive. It means this isn't just a bespoke lab experiment requiring decades of brand new tech to build. It's a practical reality that can be scaled up quickly and efficiently. So, the crucial point is this. By solving the translation bottleneck between microwave and optical domains, this breakthrough connects distant processors with minimal loss. This single advancement directly unlocks the scalable quantum internet. It literally paves the pathway toward those fault-tolerant networks we mentioned right at the beginning of our journey.
To really summarize the sheer magnitude of this achievement, the source perfectly notes that the Imagenta hybrid platform provides a practical pathway to scalable quantum networking infrastructure that connects distant quantum processors with minimal loss. It takes the vision and turns it into an engineering reality.
Bridging the gap with thin-film lithium niobate defeats acoustic noise and preserves fragile quantum information. It is absolutely the key to scalable networks. Which leaves us with one final thought. With the greatest bottleneck to quantum communication officially solved, how soon do you think the unhackable, hyper-fast reality of a global quantum internet will actually reach your devices? Thanks for joining me on this explainer, and I'll see you next time.